Welcome to The Explainer. Today, we are tackling one of the biggest questions you can possibly ask. Where did all of, this come from? We're going to dive into the incredible evidence that helps us piece together the origin story of our universe. This question has captivated people for, forever. And today, modern cosmology has a really powerful, evidence-backed answer. It's a story that unfolds over an almost unimaginable 13.8 billion years. Okay. Let's get into it. All right, first things first, let's clear up a huge misconception. The Big Bang wasn't some kind of cosmic firework going off in an empty void. Not at all. It was the beginning of space and time. It was an expansion of space, happening everywhere, all at once, from a state so hot and dense it's hard to even wrap your head around. So you might be wondering, why are scientists so sure about this? I mean, it sounds pretty wild, right? Well, it's not just a cool idea. It actually rests on several really solid pillars of observational evidence that all point to the very same conclusion. So, pillar number one is the fact that our universe is expanding. See, back in the 1920s, an astronomer named Edwin Hubble made a shocking discovery. He saw that pretty much every galaxy out there is moving away from us. This completely shattered the old view of a quiet, static, unchanging cosmos. And here's the really cool part. It's not random. Hubble found this direct proportional relationship. A galaxy that's twice as far away from us is moving away twice as fast. And this is key. This isn't just stuff flying through space like shrapnel. It's the very fabric of space itself that's stretching, and it's carrying all the galaxies along for the ride. Okay, pillar number two is like finding a fossil from the dawn of time. I mean, think about it. If the universe was once incredibly hot and dense, there should be some leftover heat, right? Well, there is. We call it the cosmic microwave background. It's this faint glow of radiation that filled all of space, an echo from when the universe was just a baby, only 380,000 years old. And this is where the theory just gets so powerful. It didn't just predict, hey, there might be an afterglow. No, it predicted its exact thermal signature, what physicists call a perfect blackbody spectrum. It's like the unmistakable fingerprint of something that was once in a state of perfect uniform heat. And when we finally built telescopes that could see it, the data was a flawless match. It's truly one of the most successful predictions in the entire history of science. Now, after 13.8 billion years of all that cosmic expansion and cooling, that primordial fire is, you can imagine, incredibly faint. The temperature of this background radiation today is a mere 2.725 Kelvin. To put that in perspective, that's colder than liquid nitrogen. It's just a whisper of warmth above absolute zero, the coldest temperature that's even possible. Our third pillar comes from what was basically the universe's first chemistry lab. In the first few minutes of existence, the entire universe was hotter and denser than the core of our sun. This is when the very first atomic nuclei were forged. And the theory, it makes incredibly specific predictions about exactly how much of each of these light elements should have been created. And the predictions are just stunningly accurate. For instance, the theory says the early universe should be made of about 25% helium-4 by mass. And guess what? When we look at the oldest stars and the most pristine gas clouds out there, that is almost exactly what we find. The amounts of other elements like deuterium and lithium, they also match up beautifully. So, with that evidence laid out, let's switch to a timeline and actually see how all this builds from those very first moments into the huge structured universe that we see all around us today. Okay, so in the tiniest fraction of a second, a period of insane hyperexpansion called inflation smoothed everything out. Then, within the first 3 minutes, those first nuclei formed. At around 380,000 years, things cooled enough for atoms to form, and the whole universe became transparent, releasing that cosmic afterglow we just talked about. Over the next billion years or so, gravity started to do its thing, pulling matter together to form the very first stars and galaxies. And then, something strange happened. The expansion started to speed up. But here's the thing. For everything we figured out, the Big Bang model has also shown us just how much we don't know. It's taken us right to the edge of our understanding and basically shown us this vast, dark ocean of cosmic mysteries. And honestly, that's where the story gets really interesting. So look at this. This is one of the most humbling charts in all of modern science. It turns out that all the stars, all the planets, the galaxies, the gas we can see, everything we are made of, that makes up less than 5% of the universe.
The other 95% is made of two things we can't see and we barely understand.
About 26% of the universe is something called dark matter. We can't see it, we can't touch it, but we know it's there. It provides this extra gravitational glue that keeps whole galaxies from just flying apart. It's like the invisible scaffolding that all the cosmic structures we see are built on. And then there's the biggest slice of the cosmic pie, nearly 70%. And it's even weirder. We call it dark energy. This appears to be some kind of mysterious force that's causing the expansion of the universe to speed up, pushing everything apart at an ever-increasing rate. Figuring out what it is? Well, that's one of the single biggest unsolved problems in all of physics. So you see, the Big Bang Theory isn't the end of the story. It's our best description of cosmic history, for sure, giving us this incredible framework for understanding where we came from. But it's more than that. It's also a map that points us towards these vast, undiscovered territories, leaving us with the most exciting questions in all of science. What lies beyond that horizon?